Okay, welcome back, everyone. We have a very nice transition this morning. You saw functional programming and through functional style with Lean. And now Deepak, who's an expert on the other style, board style verification, will talk about that style of content proving. And then we'll, after that, have Ilya, who will talk about doing that in Lean and other things. So, Floyd Horse style program verification. Deepak D'Souza from CSA IISc, give our first talk.
Thanks, Siddharth, and thanks for the invitation to this workshop. So I should confess that I don't know much about Lean myself, so maybe I should have been sitting with you all for some of it earlier talk. But I think Ilya's talk might say something about doing whole logic proofs in Lean. Okay, so basically this is a way of, whole logic is a way of, it's a proof technique for proving correctness of programs. There's a certain notion of correctness, which is used here, which I'll explain. Okay, and I guess I don't need to motivate why we need to verify, give formal proofs of correctness of programs. In general, from a point of view of safety critical systems, giving formal proofs gives you a higher level of assurance as compared to just testing your program. So that's the motivation for us from the programming languages and systems perspective. So Floyd whole logic is basically a way of, first, I mean, it's all these things, but to begin with, it's a way of asserting properties of programs. And the property is typically something like this, which we call a Hoare triple or a pre-post condition. So here's an example of a pre-post condition. So we have a program P. Okay, we'll use this as a kind of running example in the lecture. So this program is trying to, can anybody guess what it is this program does? Adds two numbers. Which two numbers? Okay, M and N. Okay, so M and N are like two variables at the beginning of this program, so it's got some values in it. And then this program runs. It initializes the accumulator A to the value of M, and then incrementally initializes X to 0, and then keeps counting up and adding 1. So it's like adding N into M, one at a time. You might want to, assert some property about this program, saying that if I started in a state in which the variable n has value at least 0, I don't care what the other variables have, a, x, and n. But if n has value greater than or equal to 0, then we are saying that this program will, if it terminates, because there's a while loop here, it may not terminate. So this is kind of weak notion of correctness. If it terminates, then I'm going to guarantee that a, the value in the accumulator a, is exactly the value of n plus n. The sum of the values in n. Okay, so that's the kind of assertions we have. This is like a precondition, and this is a post condition for the program. I'll say a little bit more about it in the next slide. Okay, and then there is two styles of proof. Both are kind of based on the notion of an inductive annotation. And one is due to Floyd, and the other one is due to Hoare. So we go through both these techniques, and maybe the one due to Hoare is more suited for something like Lean, encoding it in Lean and trying to do proofs in Lean, because it has like a proof system, a formal proof system. Okay, and there's also another big name in this area, which is Dijkstra, who came up with this notion of weakest preconditions, and that's useful in proving completeness, for example, of this proof system of Hoare. So we'll see, hopefully we'll see all these three things. I said that earlier. It's not like the ones, but I think the one in Lean is more a functional style of program. So this is more like the C language. Okay, and we'll have 4 basic kind of statements. So there's a skip statement which doesn't do anything, not very interesting. Assignment statement, which evaluates the expression E in the current state, which is, a state is basically the values of variables of the program at that point. Evaluate E in that. So E could be, for example, x plus 1. Okay. And put its value into x. That's the assignment statement. Then there's a if then else. If this condition B is true in the current state, then you do statement S. Otherwise, you do statement D. There's a while statement. While condition B is true, keep doing S until B is false, and then you come out of the loop. And this is the sequencing of 2 statements. First do S and then do D. Okay, so I should say at the outset that the use a kind of idealized programming language where your variables are real integers, for example. If I say x is an integer variable, then you just assume here that all the variables are integer variables. And integer means not the normal integer variables that you have in your, let's say, C program, which is it's a 64-bit number between some minus something and plus something, a bounded integer, but these are unbounded integers. It was just a kind of way of looking at a simpler situation, and when you're at least developing things based on that. And if you want, you can always extend the technique to handle bounded integer as well. So this is an idealized kind of program. Okay, so to define this notion of the pre-post, the whole triple, and even other things, it's useful to view a program as a function which transforms an input state to an output state. Okay, so for example, if I took this program, which is the sequencing of these two statements, and this was my state, x has value 2, y 10, and z 3, then I can view this program as transforming this input state to this output state, where x has value 2, y becomes 11, and z becomes 4. Okay, so if this is my set of states, just picture the set of states that this program operates on. So basically a valuation to the variables of the program. Okay, then this Venn diagram is just showing the universe there, which is a set of all states. And given a state in the set of states, P will map this state to another state, again in the set of states. So it's like a function from states to states. So each state is like this, right? It maps a variable to an integer. Every state is a function from the set of variables to it's partial because
Some states it may just crash.
yeah, it might crash or it might loop. That's one problem, right? Because we have programs with loop in them, loops in them. What function does this give you from the set of states to the set of states? It's not going to terminate on any input state that we give it. So it's a partial function. Not a very interesting one, but in general, for some states you might terminate, for some states you may not terminate. So that's why, in general, we associate a partial function with it. So this is just to say, so what is a predicate on state? So we'd be looking at predicates of the form, x is less than y or x is greater than or equal to 0. These kind of quantifier-free predicates are now. Okay, and every predicate like this will give you a set of states. Okay, so we'll view this predicate, just think of it as identifying a subset of states in this universe of all states. So for example, x is 0 and y is 1 is inside here, but x is 0 and y is 0 is outside. Okay, so now what is this assertions that you can make in whole logic? So these are these four triples, also called assertions of partial correctness, because we're not worried about termination, so it's partial in that sense. So here's an example. Maybe let's look at this example here. So this says that here's my program P, and this is the precondition which says that y has value at least 10. Okay, and so if I assert this triple, x is less than equal to y, and then this program, and then this is the post condition, we are saying that if I start this program in any state satisfying this precondition, then it may or may not terminate starting in one of those states. But if it terminates, you're guaranteed to come out in a state satisfying the post condition. So just view the precondition as this set and view the post condition as another set. And you're saying that if any point here, if I run this program, either I don't terminate or I terminate in a state satisfying. So the image of this partial function is all fully inside B when I apply it on. Okay, any questions about this? This is the basic like a pre-post condition. Okay, so we can formalize when a given program satisfies given pre-post condition. So for example, I can say that this whole triple APB is true. Okay, so I can write it this way. So if the square bracket is the so-called denotation of P, or this partial function induced by P, okay, then I'll say that whenever I have a state S that satisfies A, and whenever I know that S comma T belongs to this partial function, then T should satisfy. So that is the meaning of this Okay, and in general, you can think of P, the denotation of P, not just as a partial function, but maybe a relation in general. If you want to model, for example, non-deterministic programs, so it's formulated as a relation. Okay, so some example properties that you might, some of them may be true, some of them may not be true, but you can at least assert them. So this one says that the program is checking, basically assigning min the minimum of A and B. And the precondition is saying that I don't care what state you start me in, but when I terminate, I'll say that min is dominated by both A and B. Then for this program, we've already seen. So here, let's say I started in a state in which n was at least 0, then I'm going to guarantee that if I terminate, I'll terminate in a state satisfying A0. Yeah. This one. Okay, so sorry, I didn't introduce this, but it's just another way of writing this. Okay, which is you take the, so P, think of P as a relation, right? Or partial function if you want. Right? So if I apply P on A is a predicate. If I take its denotation, I'll get a set of states. So apply this partial function on that set of states. Right? Or take its image, post image, if it's a relation, that should be contained in the denotation of the predicate B. So just another way of saying that. So you could say that also, right? So say that not only is, is this true, but you can also say that min is either equal to A or it's equal to B. So that would be a stronger post condition and something that you might want when you're reasoning about it. Okay, so which of these four triples are true and which of them are false? But what about this one? Is it true? Looks like it's true, right? Okay. And so you can try to kind of informally reason about this and say that this must be true. Similarly, this is also true, but I need to reason about this while loop and think about a lot of conditions. And for example, what would be a whole triple which is not true? Here, A is greater than m plus n. Yeah, that would not be true. Okay, and so and what do I need to falsify? Say that a whole triple is not true. Right, I just need to give you one input which is inside the precondition. So one input, for example, n equal to 13. Right? And if I can run the program and end up in a state which doesn't satisfy A is greater than m plus n, then that's a violation of this. Right? So proving that a whole triple doesn't hold is somewhat easier than proving it does hold. Okay, so the question now is what are the techniques to prove? How do I prove that this this post condition holds for this program? So you'll have seen various techniques in mathematics like induction and different kinds of things, but this is a different kind of a beast, this program. And how does one, say that some assertion should be true at the end of the program? Okay, so these two guys gave, actually it was Floyd first and then Bohr developed more on that, but they gave this idea of proof technique for such three-post condition, which is basically the idea of an inductive annotation. Okay, so what is this inductive annotation? So if you look at Floyd's first paper, the 1967 paper, he has this example in his paper trying to show how his proof technique works. Okay, so the program is like a flow chart, and the program is, I think it's adding up the elements of an array. So this AJ, this AI here is an element of an array, the ith element of array, small a. Okay, and capital S is like the sum, integer holding the sum of all those values. Okay, and so basically he shows here that he wants to show that at the end of this program, S will be the sum of all the values in the array from 1 to n. Okay, and how does he do that? He has an annotation at each point in this program. So we call these points program points. Like for example, just after start, and just before the program begins is one program point. Right? When the program ends is another program point. And after every statement, there's a program point. Okay, so with every program point, he associates an annotation. Annotation is a predicate saying what are the possible states that can manifest at this point. Right? An over approximation of the set of states that can happen. Okay, and what is an inductive annotation? Annotation is inductive if, suppose I have an annotation at this at this point, right? And then, so it's some bunch of states here. And now I do this statement in which I'm assigning 0 to S. Okay, then the resulting state, right, for each of these states should fall inside the annotation at this point. So that's the inductiveness of the annotation. So let's look at a simpler example. Okay, so here's that one of our two earlier programs we had. Okay, Y is incremented and then Z is assigned the value of X plus Y. Okay, and let's say initially I knew that Y was greater than 10, and I want to show now that after doing this, Z will be greater than X. Okay, that should hold because if Y is greater than 10 and I increment Y, then Y is at least Y is greater than 11. And then if I add something greater than 11 to X, I should get something which is strictly greater than X. Okay, so what are the annotations so there are 3 program points here, one before the program, one after the first division, one at the end of the program. So the annotations we've come up with here are these ones here. So one is this Y greater than or equal to 0. Okay, and then the other one is Y greater than or equal to 1, this other one here. And the last one is, this is the one we have, I think. The annotation here is Y is greater than or equal to 1 and Z is equal to X plus Y. Okay, so these are the 3 annotations, this one, and this one. Okay, forget about the other circles for now, the other ellipses. Okay, now why is this annotation inductive? Right, so let's check it for this statement. So the annotation at this point is this set of states here, Y greater than or equal to 0. And the annotation at this point is Y greater than or equal to 1. Right, so if I start in any state satisfying Y greater than or equal to 0, and I increment Y, then I'm guaranteed that Y will be at least greater than or equal to 1, right? Okay, so I'm guaranteed to come out in this annotation at this point. Okay, so if I'm in a point here and I do the statement, then I'm guaranteed to come out in the annotation at this point. Similarly, if I was here, Y is at least 1, and I do this statement, then I'm guaranteed to come out in this set of states which says that Y is at least 1, Y is not changed, and Z is equal to X plus Y. Okay, the value of Z will always be the same as X plus Y. Right? So that's this condition here. And once again, you can check that it's inductive with respect to this statement, because if I was here, Y was at least 1, and Y remains at least 1, I've not changed Y. And since I'm assigning X plus Y to Z, this value of Z will be X plus Y. Okay, so that's an inductive annotation. Another important thing is for this annotation to be adequate to prove the property that I wanted, right? So what is the property that I wanted? It was this one, like this precondition and this postcondition. So this annotation should be adequate. So what does it mean to be adequate? Your given precondition should be inside the annotation at your starting point. So it should imply, given precondition should imply the condition that you have annotated at the beginning of the program. And your post condition, which is this one here, which was Z greater than X, should be weaker than the annotation at the end of the program. Okay, so your annotation at the end of the program should imply the given post condition. Okay, so these are basically the 3 things that you need. Okay, and okay, so notice that if as a user, if you let's say if I as a user gave you these annotations for this program, and I gave you the given pre-post condition that you're trying to prove, okay, then you can generate these inductiveness conditions, right? Inductiveness and adequacy conditions, which I just said, right? You can write them as logical conditions like this. Okay, so for example, what does the first one say? Yeah.
Is Y greater than 1 and Z equal to X plus Y.
Right.
It's actually simpler than Y greater than 1, right? Because Z can be anything.
Right. It's stronger than what we needed. Yeah.
No, but stronger than Y greater than 1. Y greater than should be partial.
Y greater than 1, is it?
And right. Then Z equal to Z.
Right. Y greater than 1 should be part of this one. Yeah. So does that lead to some problem?
No, what I'm saying is this Z is unconstrained above Y greater than 1 in the other.
Right. Yeah.
So
Does the bottom one strictly contains the other one? I mean, is it the inductive property?
No, no. So the bottom one doesn't contain this. It contains this after applying this transformation to that set. Right? After applying the statement to the states here, then it should contain.
Okay.
So it's like you're transforming the set by applying the statement, and that should fall inside this design. Okay, so anyway, so I'm just trying to say that in this slide. Okay, so for example, what is this saying here? That if y is greater than 10, then it implies y is greater than or equal to 0. So which condition is this capturing? Can one of you tell me? Okay, this is actually trying to capture adequacy of because it's saying that your precondition should be inside the set of states that you've annotated your programs initially. So here I've annotated it with this one, y greater than or equal to 0. So the given precondition is y greater than 10. So y greater than 10 should imply my given annotation. So that's this one. Right? And similarly, the other adequacy condition would be this one here. Okay. If I'm inside here, then it should imply that my post condition is okay. And similarly for the inductiveness, for example, if you want to say that if you are here and you do the statement to come out here, okay, you can encode that in logic by saying that my state here is, let's say, xyz. Here my state is x prime, y prime, z prime. So this represents them as three new variables. And then this transformation is just saying that x prime is equal to x, z prime is equal to z, right? And y prime is equal to y plus 1. Okay, so we have imported that transformation here. Okay, and you're saying that initially if I know y is greater than or equal to 0, and now I know this, the transformation happens, and say that something is true about y prime. So these are a lot kind of logical assertions, if you want to call them that. Okay, which are also called verification conditions. So given annotations, I can generate these verification conditions and ask a logic solver to tell me, are these logically valid? So of course, I have to tell you that these x, y, z come from some domain, for example, integers. So implicitly, all these implications are quantified for all. So you're saying that for all x, y, z, this should hold. For all x, y, z, x prime, y prime, z prime, this should hold. Yeah. Right. So I'm sure Lean has its own way of doing this. If you tell it that I'm within the class of linear integer arithmetic, and then we can prove it. But there are also decision procedures for many of these things. So there are algorithms which can answer these questions. Right? Is this or is this? And in fact, in the verification community, by default, for example, Z3 and those kind of backend solvers will use decision procedures to answer this. Okay, so that's the basic idea of a Floyd kind of annotation, adequate inductive annotation. And these are the verification conditions that. So here's another example of that of our kind of running example program. So I've given the annotations here, okay, and you can check that the verification conditions are all satisfied for this. Right, so therefore so that's a good point. So why does this mean if let's say I have an adequate inductor annotation for my program for a given pre-post condition? Why does it mean that the program must satisfy this pre-post condition?
It's the chain of application.
Okay.
So we eventually get to the precondition in place of the.
No, that's not.
After applying the program, you will get something.
So it's not a sequence of statements, right? There's a loop in it, and you could go through the loop several times. So what is the key observation here, which says that this is an adequate? It's an argument which should convince someone else that their program satisfies. Yeah. Invariant? Right. So in a sense, these annotations that we have given initially are invariants of the program at those points. So what does invariant mean? To take any execution of the program that starts in your in the given precondition, right? Any input any execution which starts with a state in the given precondition, right? And now you run your program. Then the annotations that in this, if they are adequate and inductive, it is guaranteed that every state that you go through in this execution of the program, right, at every point. So for example, let's say I started here with all the values 0. Okay, then here also I'll come out in a state in which all values are 0. Right? So that all values of being 0 will be here in this state, right? Because all I wanted was n greater than or equal to 0. Right? It will also be here because right, in this annotation, just to check that n is greater than or equal to 0 and e equal to 1. So all zeros satisfy this. Right? So as the execution goes through this program, at every state, the state is going to be in the annotation that you have built. And that's easy to see by induction, because initially, if it's a length 1 execution that just starts there, then by assumption it is going to be in your, because a given tree is contained in your annotation at that point. And if it's a length 2 sequence, then because the previous one was in the annotation here, and this annotation was inductive with respect to the one here, this state should also be contained. So you just use your these properties and show that if you start the program in a state satisfying this initial precondition, you're going to visit states at every program point that fall inside the annotations level. Okay, and in particular, when you come out of the program, okay, it'll be easier to see here. When you come out of the program, you're guaranteed to come out, if at all, in the annotation at that last point. But the last point annotation is within your given post condition. Right? So that says that you must also satisfy this. So that's the basic idea of Lloyd. Okay, so I think I just have about 10 minutes left. Let me quickly tell you, there are some exercises in the slides here which you can try. Okay, and let me just mention that typically in verification, like for example, if you look at the tools that implement of flow verification, like VCC or Framas, you might have heard of these tools. Right? You don't have to give annotations at every point, but it's enough to just give it at for every while loop. So more generally, if it's a nested while, you just give me annotations at these points, and then I can generate the verification conditions for just to be analytic and that way. Okay, so now let's look at Ho's technique, that is Floyd's view. So Ho's taken a slightly different view of the program. He's saying let's look at it as a structured program, which is basically the composition of statements. Right? So this program, I can view it as the composition of S1 followed by S2 followed by S3. Okay, the S3 is a compound statement itself, that's the while of the composition of two other statements. You can think of any program as a sequence of statements. Each statement might be also a compound statement. It could be a if then else or a while loop with further nested structure. If you were to represent a program in Lean, maybe this is the right way to do it, right? It represented as a sequence of terms. Each term is, one of these constructs made out of simpler words. Okay, so Hoare gave these axioms, okay, or proof rules for deriving Hoare triples. So, as an example for this swallow running example that we have, right? If I were to derive this Hoare triple, so there's a precondition, and this is the simpler one. This is a single statement program. Okay, then I can write down a sequence of Hoare triples like this, right? Such that, let's say, the last one is the one that I'm trying to prove, right? And each one before that either follows by a axiom, right, or by using one of the proof rules. So these are the proof rules that Hoare gave. Okay, so one is, let's forget that. For example, the skip statement. So the way you read these rules, for example, here is, let's say, for the if then else statement, right? This is the one below the line is the Hoare triple I want to prove, right? And the program is just this, right? If B, then S, else T. S and T may themselves be complex programs, compound programs. Okay, but I want to prove the Hoare triple for this if then else statement. Okay, then 4 is saying that it's enough for you to prove the thing above the line. To prove the thing above the line, you can conclude the thing below the line. And so what does the thing above the line say? That in this case, it says that if this 4 triple is valid, right, and if this 4 triple is valid, right, then you can conclude the law. So intuitively, it is saying that if I know that from the P, sorry, I just switched to notation here, but P is a condition. P and Q are conditions here. There are programs. So if condition P and condition B hold, right, and doing S takes me inside Q, and similarly, if P and not P, whatever it holds, I do, and I do P, I go inside Q. Both cases I go inside Q. Then I can say that if I start in P and I'm doing FD, then S sells T, and I will stay inside Q. So that's the flavor of these proof rules that he gives, right? So for example, for skip, without any assumptions, if I start in a state satisfying the predicate A, then I'm going to continue to satisfy the state predicate A. Okay, the assignment statement is, so what does it say? That if I have a statement X is assigned E and I want to show some post condition A for that, okay, then just take this, the predicate A, okay, and replace every occurrence of X by E. So read this as A with E for X. Okay, E is, for example, think of E as X plus Y. Okay, so X is assigned X plus Y. So in A, you replace every occurrence of X by this expression. Okay, so for example, here is a so here's an application of that assignment rule. Okay, so the statement here is X is assigned X plus 2, and so E is X plus 2, and the post condition is that X should be at least 5. And so what should be the preconditions? Such that when I do the statement, I come out in a state satisfied X is greater than 5. So if you think about it, it's basically saying that X should be at least 3. Okay, and you can get that by Ho's rule by saying, in this post condition, you replace every occurrence of X by X plus 2. So this becomes X plus 2 is greater than or equal to 5, which is effectively X is greater than 2. So intuitively, this is true because, I mean, how do I establish this post condition? Because I'm only changing the value of X like this, right? So basically, this condition should hold before the statement itself, except that the value of X should, I mean, the value of X is changing by this value, right? And then I want this condition to hold. Right? So basically, if I plug in this new value of X in that post condition, that is a precondition which is equivalent. Okay, so in a sense, these are also the kind of weakest precondition that will establish the post condition A, where you are doing the statement X is M. Okay, if that else you already saw. So the while loop is the interesting one. Okay, so I want to prove something like while B do S for this while program, while statement. I want to show that if I start in a state satisfying P, then I will come out in a state satisfying P and non B. Okay, then
Here's the question.
Yeah, right. So that's one example program there, right, which may not dominate. Right. So for such a program, you can start with right. This has not dominate. Right? But for example, in this program, you can give any post condition, like any precondition also. Pretty much. Because you're never going to violate it because you're not dominating and coming out on it. Yeah.
So can you see that each of these attachments say if that program terminates, then the post conditions.
Right. Each of them says. Right. That's it. Yeah. So it's Okay, so let's just look at the while loop condition. So it says that if I'm in a predicate satisfying, let's say I'm in the set of, so for the while loop, if I want to conclude this, the rule says you prove that essentially this capital P is a loop invariant of your while loop, okay? In the sense that if I'm inside P and inside the loop condition B, and I do S, which is the body of the while loop, okay, then I will come out in a state satisfied. Okay, so this is for the while loop that you're looking at is like this. The rule says that you try to show that P and B and this 4 triple is true. Okay, so graphically it looks like this. So this is P. Let's say B is the while or the loop condition for a while loop. And if you're inside P and B, and you transform the state by a program S, which is the body of a while loop. And let's say you come out with a state here, then the state has to be inside B. Okay, that's what this statement was saying. That's the assumption above the line. Okay, and then the rule says that if you can prove this, then you can conclude that your while statement satisfies this pre-post. Essentially, this is true because if you started in P, then either you're in a state which is outside B or inside B. If it's outside B, you'll immediately come out, but you're still coming out inside P and not B. Right? And if you were here and then you're guaranteed because of this assumption, you're guaranteed to come out inside P again. Right? So either you keep coming out inside P or you'll eventually come out in a state satisfying P or not, if at all, or you continue. Okay, and right. So there are these rules like this, and I've given an example proof here of this one. Just proves that if x is strictly greater than 3 and I do x equal to x plus 2, then I'll come out in x greater than negative 5. Yeah, this is the full proof and whole logic. So what is the proof and whole logic? I give you a sequence of statements like this. Each statement is a whole triple, and each statement is either one of those axioms, or you get it by applying a proof rule to some earlier things that you have. So it's very similar to a proof that you would do in mathematics. So, Siddharth, what's the... Okay, so the important question is, let's say I have a program, right, and I want to do a proof of its correctness using whole logics, using this proof system. Right? How do I go for sure that there is a proof of, right? There's the guaranteed to be a proof of this statement, this assertion. Let's assume I know the assertion is true. Right? Is there guaranteed to be a proof of this assertion and whole logic? So that's a completeness question which comes up in the mathematical proof system as well. Is a proof system, complete in the sense that it can prove every true statement? Okay, and so the answer is true, but like with some caveats. Okay, so for that, I need to tell you what is this weakest precondition. So given a program like this with a post condition here, okay, what is the weakest precondition for this program with respect to this post condition? Okay, so it's a valid precondition, right? In the sense that if I started in that precondition and I ran this program, I would satisfy this post condition. Right? And it should also be the weakest such. And every other valid precondition should be contained inside this. So that's the weakest precondition. And this notion was due to Dijkstra. Okay, but so for example, for this statement, x is equal to x plus 2, if I want to establish x greater than or equal to 5, then I have to, the weakest condition is that x should be at least 2. And similarly for this while loop, if I have to establish that while x is less than or equal to 5, if implementing x, if I want to establish that x is equal to 6 at the end of this, then the weakest precondition turns out to be x is less than or equal to 6. Because if x is equal to 6, I'll come out and I'll satisfy this. If x is less than or equal to 6, I'll go on incrementing till I reach 6 and then I'll come out. So it's a valid precondition. You can also see that there's no other state that if you start in, for example, if you started in a state greater than 6, let's say like 10, then you will come out in 10 and you'll not satisfy. This is the weakest set of states which establishes the post condition. Okay, so the completeness of a whole logic, or so-called relative completeness, says that whole logic is complete in the sense that if APB is a true assertion, then I will find a proof of it. There exists a proof of it in whole logic. So it's complete provided these conditions hold. So one is that the big thing is that logical language that you're using. There's X is less than Y, or maybe you have board, or maybe you have arrays, or whatever. There could be complex logical language that you're using. Provided that logical language can express every possible weakest precondition for every possible program. I mean, for every possible program and every possible postcondition expressed in this logical language, right? The weakest precondition should be expressible in this language. So if that condition is true, then whole logic is complete. And the proof is a fairly simple inductive argument to take the structure of a program. So the simple cases are that if the program is just skipped, okay, then by the skip rule, I know that I can write B skip B as a assumption, as an axiom, right? And I know that A implies B because if this O triple is valid, right? Every state in A must also be in B, because the program just transforms that state to itself, right? And if this is a valid O triple, then every state in A has to be in, right? So A should imply B, right? And therefore I can write down a proof there. And then similarly, the only tricky cases for the while condition. And the key thing here is to observe, this is where the assumption also comes in for the weakest precondition. But if you take the weakest precondition of this while loop with respect to B, okay, then that is also a valid loop invariant for this program. And therefore, you can use the inductively, you know that there is a proof of this in whole logic, and now you can use the whole rule of the while loop rule to conclude. It's not a very difficult proof to argue concludes. Okay, so let me just stop by, conclude by saying a few things. So one is there are a lot of extensions of this whole logic. So we've seen very simple programs, but typically programs have function calls, they have different procedure. So how does one reason modularly about that? And one could use this notion of function contracts, which many of these verification tools have. Your program could use arrays, right? Or more generally, they could use heap data structures, like you're reasoning about a linked list or a tree. Right? And then how does one extend the logic, the basic whole logic to address this? So these are some pointers to that. I think the main challenge is, at least from a practical verification point of view and using Floyd whole logic, how do you magically come up with this loop annotations of function contracts, which are adequate to prove what you want? People have tried various techniques. I don't want to mention that, but there's a lot of techniques that try to use data-driven learning based on examples and counterexamples. What should be there in the loop invariant and what should not be there. Based on that, you try to learn a predicate that will act as a valid loop adequately. And of course, in the case when you want to look at automatically proving, at least discharging the assumption, discharging the verification conditions that we generate to a program, that you want to be within decidable fragments of logic. So if you're reasoning with arrays, then there is this array property fragment which gives you a decidable fragment, bit vectors and so. Okay, and there are some techniques that with scaling to large programs is a big problem. Coming up with multiple invariants and checking these, all these are challenges for the verifier on the servers. And there are some kind of notions of lightweight verification where you try to say, okay, I'm not going to prove everything, but I'll prove part of it and I'll test some other part of it. So that's this verification model of testing is at the front of it.
Okay, welcome back. We'll turn to the anchor session, highlight session of this summer school. We have Ilya from National University of Singapore, who will today we'll talk about monadic verification. I guess you're doing well, but
yes, thank you. All right, so this slide is actually the second slide of my presentation. I will keep it here for another couple of minutes, so you would have a chance to, if you want to have some interactive experience, so you could go here, clone this repository, switch to this branch, and execute that, and then open that in the VS Code, which will give you the advertised monadic verification experience in Lean, and we are going to talk what it is. And while you're doing that, First and foremost, I want to thank Professor Siddhartha, who invited me here. I'm enjoying my visit hugely. It's my third time in India in my life and second time this year, and it never disappoints. It's a beautiful campus, wonderful food, and you guys even prepared a nice weather. So thank you for that. Very well. All right. So I actually was planning to give this talk tomorrow, but the lecture by Deepak where is Deepak, by the way? So has prompted me to switch because, believe it or not, we are going to see some Hoare logic, and we are going to see how to verify imperative programs in Lean. So yeah, the same Lean in which you can write functional code and you can write your favorite mathematical theorems. And what hopefully we will learn today is that actually it's not that difficult to encode everything that you care about in so-called mainstream realistic programming as mathematical objects in Lean. And that gives you a way to verify the programs and the languages that, well, you actually care about, like Python or Java or C in Lean itself with the ultimate guarantees. So the title of the talk is Velvet, a multimodal verifier for imperative programs in Lean. So I've already said that we are going to do verification of imperative programs in Lean. Velvet is the name of the tool. This is just a name. There's not much to it. But I want to dwell a little bit on the idea of multimodality and verifier. And first and foremost, we are going to see what exactly we mean by building a verifier, what a verifier is, and what's the difference between Lean and a verifier that is built on top of Lean. And second, we are going to talk about so-called multimodality. Those of you who are AI-minded might think, oh, that might be like multimodal foundational neural nets. No, that's different. Multimodality, I'm sorry to disappoint it. This is a relatively new term. It's not coined by me. It's been around for maybe like 10 years, but it's still relatively uncommon. So I'm going to explain that. Okay, so if you didn't download it, that's fine. I'm going to give hands-on demo. There will be quite a bit of live coding. So I understand it's afternoon. We had a lunch and 2 teas and some samosas. So if you feel like you have an urge to ask a question, please do that. Raise your hand, make yourself loud, because that's the only way we don't fall asleep in this last lecture of the day. All right, so gentle reminder, courtesy of Deepak, Floyd-Hoare logic, that's what we've just seen. Hope you remember everything that he has said, because that's going to be very important. We are going to build directly on that. But if you don't remember anything of the Hoare logic, just try to remember these 3 lines. The exact wording is not important, but Hoare logic is the way to make statements about imperative programs. And there are multiple ways you can make statements about imperative programs, but typically imperative program is something that manipulates with a state. State can be understood broadly. Stack, memory, even input-output channels can be thought of as a state. It's actually a surprisingly rich concept. So if you want to reason about stateful programs, inevitably, this is something that you will discover even if you try to reject the idea of Floyd-Hoare logic. That's the best way to say certain things about imperative program is to say what exactly is the state that we are going to run it in. So it doesn't have to be in concrete state, but we say if we run a program S from a state that satisfies certain property, then good things will happen. It will not crash. And upon its termination, if it does terminate, it will end up in the state that satisfies the property Q. So this is a semantic definition because it refers to running the program and the program terminating or not terminating. It's a semantic definition which is much concisely captured by idea of a Hoare triple. So this is effectively just syntactic sugar, a shortcut to say exactly what these 3 lines in bold say. So and then we have seen plenty of examples. I'm not going to discuss in too many details what we have here. So these are very primitive single statement programs. Obviously, we can scale it up. And we have seen the rules that scale it to conditionals, to loops. And well, this is actually something that surprisingly well works even for realistic languages. There are many implementations of this idea of Hoare-style specifications with pre and the post conditions that are implemented for mainstream languages. Okay, so how exactly is this all related to Lean proof assistant? And what Lean can provide so we can encode our programs into something that Lean can verify. So the answer comes from one of the greatest computer scientists who ever lived, Edgar Dijkstra. The same Dijkstra as of shortest path algorithm, and this name has been mentioned last hour in the context of what's called weakest precondition calculus, which is probably one simple yet non-trivial idea that makes core logic just work. So, and we will see how exactly it works and why this is such a good mechanism to go from ways to specify programs to actually do something useful. So this is a seminal paper from 1975. The crazy thing about this paper is many other greatest papers in computer science that have been published between like late 1960s and 1980s. It's amazingly short. It's 5 pages. So nowadays you need to write 25 pages of slop to get your paper accepted to a premium conference. Back in the days, 5 pages. And this is one of the most important papers of the last century in computer science. And funny thing is the most important part of it is this last sentence of its abstract. For the formal derivation of programs expressed in terms of these constructs, a calculus will be shown. And this is calculus, what we know as the weakest precondition calculus or weakest precondition Dijkstra transformer, which sounds like a mouthful. So when I give a lecture on Hoare logic and why Hoare logic is actually not something for boomers, but something that really matters, I show this program and showing how we can actually turn verification of this program into something fun. So what exactly this program does, I don't know. I don't care. That's probably the most useless and boring program ever. But that's kind of the whole point of verifying programs. So we say what the program does in terms of precondition and the post condition, and we forget how the program does it. Because now we only have these pre and post conditions as the specification. Our specification here in blue, so sorry for the small font, I didn't realize it would come out that small, says if we start without assuming anything about the variables this program works with, so we have A, B, whatever, we don't care. So anything, A, B can be anything. By the time we end this program, what is stored in the variable res result will be equivalent to this implication. A implies B. Okay, so this is a program. Actually, it's relatively simple. It doesn't have loops. It has conditionals. So you can remember that we actually had rules for conditional statements and we had rules for assignments. So all that has appeared in Professor Deepak's slides. So let's try to think more like engineers and try to think what this program actually does to its state and sort of interpret it backwards. Because you see, this is what we want to get at the end. So this is the formula that needs to hold at the end. If we take one step backwards, what's going to happen? Well, we need to replicate this formula and put it here. So this is exactly the same formula. I'm making very, very like small baby steps here. So and this is the formula that appears at the end of this branch and the end of this branch of this if expression. So both branches should finish and give us the same formula. So far, so good? Good. Okay. So now the interesting stuff happens. Let's focus here. So here we are talking about res. Right before we assigned true to res, right? So this kind of gives us the knowledge that at this particular point, res is just true, right? Okay, so let's capture that and write it up here. So this is something that should hold at the beginning of this branch. Okay, moving on here. So now we are here and we now need to go to this inner if statement. So we still have this. So let us replicate it to the ends of these two branches. We have done that already, nothing new. And we are going to do the same trick. So we are going to replace backwards what we assign by the right-hand side of the assignments we have assigned, right? Because at the end, you see what the point is that we will kind of bubble up the entire effect of the program to the very first line. So, okay, now since this res was assigned false, from here we go here. And since this res was assigned true, we go here. Okay, so now important part is that let's look at this if right here. So we have this formula in the then branch, which should hold at the beginning. And we have this formula, which should hold at the beginning of this branch. But we actually don't know which branch we will take depending on the B. So we don't know anything about the B on arrival. So it might be true, it might be false. So we need actually to account for both possibilities. Both possibility means conjunction. So, and the fact that we need to conjoin that when B is true, this should hold. When B is false, this should hold. That gives us this formula that we write exactly here. So I'll give you a few seconds to process this formula, but there's absolutely nothing surprising here. This is just us knowing how conditional statements work. We construct this formula backwards. Okay, now we have this formula at the beginning of this branch, conditioned over A, and here we have this formula at the beginning of the complementary else branch. And you know what we are going to do? So we are just going to do the same trick and say if, so A implies what we have at the beginning of then branch, and not E implies what's in the beginning of other branch. So now look at this. This is a logical formula. It's a formula in propositional, even Boolean logic, because all our variables are Boolean. Does it have to do something with imperative programming? It doesn't. Isn't it beautiful? We just reduced the specification of the program and the program itself to a logical formula whose validity we need to prove. And by validity, I mean, oh yeah, there's this thing, right? So this is what we assumed initially. Now, what we need to show is that this implies this for any values of A, B, A and B, and the result is God, right? Okay, so these are the formulas that the humanity knows how to attack, right? Because we have built SAT solvers and we have built SMT solvers in case of Booleans. If you need to like do something outside of Booleans and like talk about arrays, integers, and whatnot. And what SAT solvers and Boolean solvers are really good at doing is giving them a formula with a bunch of variables and telling whether there is an assignment of these variables to, in this case, true and false, that makes this formula true. So we can actually rig this process, negate this formula, and ask the SAT solver to prove that. See what's happening? So if we ask the SAT solver to prove the negated version of formula, what kind of result do we want? We want unsat, right? So we want to know that there are no solutions for which the negated version of this formula becomes true. Which? De Morgan. So which means that for any values A and B, the unnegated formula actually holds true. Okay, that was the crash course on automated program verification. This is literally how it happens. So the whole science goes down to interpreting, effectively compiling your program and its specification to a formula that some solvers can tackle, see the hand, and then just running those solvers and hoping that you will get unsat. The great thing that if you don't get unsat, you get a counterexample, because that is exactly the substitution of the variables, which violates the alignment between your program and specification. So which means either your program has a bug or, surprise, surprise, your specification has a bug. That happens too. But this is the crux of decidable verification. And this is how effectively tools such as Daphne, Verus, JML, they all work, except they build not on SAT solvers, but on SMT solvers. You had a question first. Notables. So for loops, things are slightly more complicated. So for loops, so here we were inferring the weakest preconditions, right? So for the loop, we have while B, C, and we want to know what's the precondition of that with regard to the post-condition Q. Then the weakest precondition for that is actually surprisingly difficult to get. So I don't want to get into mathematics, but what we can do, and this is actually a mathematical definition. So if we define this function of x, where x is a proposition, so this or E and the weakest precondition of I think E with regard to x, pretty horrendous. Okay, so we see it's a function of x, x is a proposition. Then we need to find x such that f of x is equals to x. That's called fixed points of the function. Okay, fixed points are that. So there is like the whole area of mathematics called domain theory that tells how to reason about them, and typically it has to do with monotonicity, great slow fixed points, least fixed points. So humanity came up with a better way. Instead of solving this equation that we don't always know how to solve, what we can do, we can guess a good approximation of the weakest precondition with regard to given postcondition of the loop. And that is usually referred to as a loop invariant. And the loop invariant is the property that needs to satisfy the following thing. So it needs to be such that if we assume this invariant holds and the Boolean condition is true, then after we execute one iteration, the invariant still holds. You can think of it as a step of induction. So loop will be unrolled God knows how many times. We cannot say statically, but this is one step of induction. So second thing we need to know is that if we finally exit the loop and we know that at the end of each iteration the invariant held, then what should be the case? Yeah, so Q. This should hold. Okay, so the invariant like this is called it's not the weakest, but it's a valid precondition for the loop. So you can effectively use it as a weakest precondition, plug it into the rest of the reasoning, and make sure that ultimately you bubble it up, and it is implied by the precondition. So this is actually what makes verification of programs with loops nasty and equivalent to halting problems, so undecidable and yada, 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 because this is actually something that needs to be guessed. Humans are amazingly good at guessing those things. LLMs are even better. So this is something that we are going to exploit big time. But great question. Lots of human energy and brain power has been spent on finding out good algorithms and heuristics to guess these things. So the question is, do we always go to an SMT solver? The answer is yes. It's very difficult to beat production quality SMT solvers. If you manage to do that, then probably you want to write a paper about bus decision procedure on a fragment of the logic on which you manage to feed SMT solvers. That there is conferences like CAF or ATVA or FSTCCS, they will love it. The point with SMT solvers is that when they work really well. So, I mean, this problem is very much NP complete, and yet the humanity has absolutely no problem solve it in any practical case. So adversarial cases are very rare. More questions? Okay, so can we all agree here that this is a statement that, okay, SMT solvers aside, this is a statement that we can write as a Lean theorem, right? Obviously, this is a stupid program that only manipulates with Booleans. But if your program manipulates with lists, arrays, and your favorite data types, never mind that it's imperative, we can still reduce its verification to proving a Lean statement. And furthermore, since these programs often have branches, and they have, this is also a conjunction of two facts, right? So each process, if each verification task will be reduced to proving a conjunct of a bunch of facts. So which means that we need to prove each of them individually and make sure that all of them hold. So each such conjunct is typically referred to as VC, not for venture capitalists, for verification condition. So when you hear about verification condition generator or VC gen, that's effectively a process of taking the specification, taking the program, and producing a bunch of conjuncts that then you can treat individually each as a Lean theorem, or a theorem in your favorite proof assist, not necessarily Lean. So as you can imagine, like we haven't really tied any of that to Lean. Okay, so the next thing here is that's pretty much all you need to know about automated program verification. So the one thing that I'm going to mention, I'll probably not talk that much about it unless someone asks me specifically, and please do it after the lecture, is that this process that we have just mentally have done by running the program backwards in order to compute in the post condition, that can be seen as a very quirky interpretation of the program's syntax itself. So when we say about program interpretation, we typically think, okay, provide some concrete values A and B, run it. But that's just, program is just a piece of syntax, right? So you can interpret it in different ways. And we have just interpreted it in a different way by sort of symbolically running it backwards and deriving this weakest precondition. So that surprisingly can be written in a Lean style that is supported by its do notation, and this is where monads came in. So this is a school on monadic programming. That was monadic programming. Let me not talk about it for the rest of this lecture. I'll give a reference if you want to understand the mechanics of that more. And basically, the upshot here is that once you realize that this is something that fits into the idea of monadic programming, you don't have to write this passes again. So you can just reuse the machinery that is defined once and for all. That's very general. Okay, wonderful. So what we have seen is a take on automated program verification. And well, obviously, many people have read Dijkstra's paper and they realized, wow, this is amazing. So we can just verify lots of code now. And they started to build tools That pretty much all are constructed around this idea. I'm going to here because if you want to write a program in C with pointers that ls, the weakest precondition approach will not quite give you the best formulas to prove. So there are other approaches to do that, but weakest precondition calculus is by far the most dominant. So tools like Daphne, which many of you have heard of, it's probably one of the best automated program verifiers. Verus is, I think, the best one that you can have for Rust. And sadly, that doesn't support Lean. So, I mean, for Daphne, I mean, just look at what we had. So you do the pre-post conditions, and you do the invariance. And that's exactly what Daphne gives you. Yeah. So we'll see the syntaxes will be very similar to Daphne. So Viper is kind of a general framework, which is more like, rather than a particular language, it's something that you can compile to. It's a very good intermediate representation. You can think of it as sort of like LLVM, but for building verifiers based on the idea of the weakest precondition calculus. So we have instances of Viper such as GoBro, which is for Go, Prousty, which is also for Rust, F-star. So F-star actually built the whole line of research around the idea of expressing weakest precondition calculus as a very specific traversal, a monadic traversal of the program, and fittingly named Dijkstra monads. So that's the name that, well, it's named after Dijkstra, but it's also came out 20 years after Dijkstra passed away. Liquid Haskell is the very same idea, but for Haskell, I mean, those are like very actively maintained tools. Okay, now going to formal methods for ontology. So JML, Java modeling language, apparently still alive and kicking, but I don't know anyone who is using it except for folks who publish at software engineering conferences, and they need something to verify Java, and they like very averse to the idea of building verifiers down. Boogie, I don't think this is official logo. This is what one of my PhD students came up with, because Boogie is like Boogie Nights, so let's have this disco ball. So this is actually something that is an intermediate language beneath Daphne. So Daphne is the one that builds on it, but there are others. Tamarin for security protocols and Proverif also for security protocols. Those are for very specific classes of programs, not general purpose, but rather something that defines authentication protocol. So Tamarin, by the way, has been like amazingly successful in verifying authentication protocols for MasterCard and Visa. So, but if you don't do security research, chances are you haven't heard of it. Okay, so this is what's called automated or auto-active verifier. So basically, the only interaction they require from you once you have the program is to write down your specification, write down your invariance, and the rest is magic. So you will not have to write the proof, which is what you've spent this morning doing in Lean, right? So you are writing the proofs. Is it a good thing? Well, definitely, it's a good thing that you don't have to write the proof. The problem is that life is complicated, and as we all know, there are statements for which there are no automated decision procedures. So certain things, I mean, if everything could have been proven automatically, P versus NP would not be a problem. So, and actually, no, like, and probably the world wouldn't exist as we know it. So it's probably a good thing that we cannot prove everything automatically. But sometimes we want to prove things outside of the stuff that SMT can do automatically. So, okay, so this is a very short picture of what is happening. I already explained it. So take the program, take the specification. This is literally what Daphne syntax looks like, very small, but requires a precondition, ensures those are two different conjuncts. In the post condition, these together with the program goes down with the way we will see it to one of the SMT solvers. The de facto ones that are best is Z3 and CBC5 from Microsoft and Stanford and collaborators correspondingly. And then either CBC5 says unsat, which is great, so your formula holds for all the variables, or it gives you the concrete instances of the variables, because again, SMT solvers they prove existential statements, and that you should interpret as a counterexample, which means either your program or specification has a bug. More often than not, however, there is a third outcome when SMT solvers just time out. Because, and again, it's probably nice that I'm giving this talk in IIC, because as you know, there are very, very undecidable fragments of first order logic. So like effectively propositional logic, great. If you are in there, it's always yes or no, and there's a decision procedure. If it's alternation of quantifiers for all exists, then, well, practically forget about it. I mean, you can write this formula. It's going to be in first order logic. SMT will accept it as an input, but it will most likely time out for like very fundamental reasons. So what do we do in this case? Well, sadly, this is where the interest in mathematics stops and like lots of hackery begins. So the tools, they give you some ideas they give you some mechanisms about how to sort of like guide the search for proving this formula or proving that the formula is unsat. And you start learning about things such as triggering and equality saturation, which I'm not sure you want. So much for automated theorem proving. What would be really nice is if we could somehow go to the proof mode where LeanLang gives us. So, and you see where I'm going with that. So that's exactly what we are going to do. But before I do so, let me just point out that besides automated tools, we also have interactive program verifiers. And well, here we have a general purpose frameworks, COC, nowadays known as ROC. We have, Alina is not on this slide, but it's going to make an appearance. So we have Isabel Ho. And we have much more specialized tool sets, which are nice because they are not standalone verifiers, they are libraries embedded into this verifier. So for example, VST is something that has been developed over 15 years at Princeton to verify C code on top of ROC. And Iris is a very general framework to implement, well, effectively core logics, but for languages with lots of non-trivial features. So we are talking concurrency, effect handlers, well, and probabilistic choice and stuff like that. Okay, so the point about all these provers is that practically nothing is automated. So you have to write the proofs even of trivial statements like you've seen manually unless you have bothered to implement a tactic for that, which is a huge downside, but the upside that you're always in control and you always have the most comprehensive way to absorb your proof. And obviously, like this part of the world, this part of the formal methods field has been bashed relentlessly over the past 2 decades for being so laborious and not scaling. And then the LeanLang came, and see who's laughing now. So, but let's talk about this later. So finally, so this is actually a really nice talk by Mike Dodds. So there are slides. I will share the slides so you don't have to take a picture of everyone. So Mike Dodds is a scientist at Galois, which is an American company that does contractor work in the formal methods. So he gave this talk called "And Things I Learned Trying to Do Formal Methods in Industry," which basically says why, and this talk is 3 years old, so why formal methods had so little impact in industry. Because the benefit you're going to have at the end when you have verified everything and up to your specification, everything is bug-free, is huge. The problem is that the curve is like that. So you basically have nothing until you have finished your last proof. Whereas something like testing is pay as you go. I mean, you never get 100% guarantee with testing, as you know, thanks to the extreme. But you will, I mean, and this is a common belief, like doing something like fuzzing with AFL and whatnot, you will get asymptotically very close to having no bugs. So, which for some people will be just good enough. So, and that was a problem with and that's why quite a bit of effort, and this was actually a trend again before LLMs became so good at writing formal proofs, was the trend in the formal methods community that in addition to automated verification, which is kind of nice, but has severe limitations when it comes to proving certain things, and interactive verification that can prove virtually anything, but nothing is easy. So there is also a third part, which is just bug finding tools that say, well, you know, we are not proving, well, unless proving the existence of bugs is your idea of proving things. Yeah, I mean, existential quantification is very easy to prove if you know what you're looking for, right? So this is what the so-called dynamic analyzers, which is a fancy name for glorified testing, do. So quick check is probably like one of the finest examples. Like testing versus verification rift aside, this is a fantastically elegant idea of generating, like creating generators for random data monadically in a functional language that has been ported to virtually any language. Like if you can think of language, it has a version of QuickCheck, which generates a lot of data. And this is what functional programmers do for fuzzing. TLA Plus, very useful in industry for verifying distributed protocols. We are going to talk about it tomorrow. Jepsen for randomly crashing systems, thereby detecting partitioning bugs. And Facebook Infer, which is technically a static analysis, but also, in fact, is a bug finder. There's obviously a huge space. At this some point, I just got bored to find more icons of the tool. So yeah, so there are many tools for testing. So what we want to have is actually we are interested to build the software, but we are interested to build a software that is correct, but maybe correct eventually. So when we develop it, we don't want to fight with the limitations of SMT solvers, and we don't want to fight with the need to prove every single thing. And actually, we might want to test it, and then we might want to try to prove as much as possible automatically, and eventually, what is not proved automatically, we want to prove interactively. Can we have all of three? And the answer is yes, we can. And this is our North Star, the idea of having what's called multimodal verification, where each mode refers to the way you validate your software and a different trade-off in cost, benefits, and the guarantees. Testing, automated verification, and interactive verification, trifecta. So maybe there are other modes, but these are the three that just come up so often that the whole tools are built around them. Okay, so what we're going to do is to show how to build all these three into Lean. And I mean, okay, that might sound like something like very difficult to achieve, but in the nutshell, challenge boils down that if you model your programs in Lean, can you run them? If you can, you already covered this one. Second, if you want to verify them with something like a weakest precondition calculus, can you have access to automated tools like SMT? And if you can, you already covered here. And finally, if you do things in Lean, just by virtue of doing this in Lean, you are here. So you see, we actually get that, like all of this mostly for free, but choosing the right foundations and also choosing the style in which we are going to encode them. Okay, so this is our goal. Okay, so there's some animation, which I have already narrated. Okay, so and just to very quickly show why there is an interesting research challenge in designing a framework for building verifiers. See, it's kind of meta. So we are not building a single verifier for a language. If you want to give sort of harness for building verifiers that you can use for your favorite language. And I'm going to give second talk tomorrow showing a second verifier built using the same approach. So when you start looking closely, is what does it mean to build a verifier for programming language? Turns out that there is a whole bunch of aspects that you want to kind of think. First of all, how are you going to encode the state? So we have seen functional programs. They're pure, they don't carry the state. And how are you going to interpret the state? Are you going to interpret it concretely, something that you run, or something symbolically, something that corresponds to a formula? Concrete interpretation is something that we use to execute the program. Symbolic interpretation is something that is useful for implementing the machinery such as weakest precondition transformer. So we want to have both because we want to have both proving and running capability. How to treat termination? So it has been discussed that in Lean, by default, all programs terminate. Sometimes program might not terminate by design. Sometimes programs might not terminate because we actually don't know whether they terminate or not. So good luck proving termination of the collapse conjecture. So we obviously want to support reasonable programs that do not terminate as well. How do we treat bugs? If we want to prove that a program has no bugs, that means that that's one reason mode. But if we want to show that the program probably has a bug, that's another mode. And this is actually the mode under which tools such as CDMC and other bounded model checkers work. So, and actually this is something that developers love because oftentimes the fact that you cannot verify a program doesn't necessarily mean that the program has a bug. Maybe your specification is wrong, or maybe your verifier is not powerful enough. But if you are able to demonstrate to the user that your program has a bug, that's actually a very powerful message. And Facebook Infer, the one which had a turnstile in its logo, that's actually a tool that is built around this idea. So again, how you're treating bugs, that's another aspect. There are others, like, for example, how you treat non-determinism. And all this seems like relatively low level, but in fact, it's nice because it gives you this multi-dimensional space in which you select the point. It usually hits one of the existing verifier tools. And when we started to look into that from this perspective, we realized, oh, wow, like each of the, like almost like every combination of these choices was implemented in an existing standalone tool. But once you start using this tool, you are committed to this bunch of choice. And this is what we don't want to, right? So you want to mix and match, and at least you want to have a library that allows you to implement verifiers as libraries that exercise different choice. For example, Daphne doesn't have runnable semantics on its own. It extracts to Java, so you can run Daphne programs, but they don't run like as interpreted. So it only has symbolic state, which is useful for proofs. It treats termination as total, meaning all programs must terminate. It's actually very difficult to write a non-terminating program in Daphne unless you are resorting to dirty hacks. It optimizes for proving the absence of bugs, and it treats non-deterministic choice what's called demonically, meaning that anything bad that can happen, it will happen. So for all means, you need to really defend yourself against all possible outcomes of randomness. So if your program has randomness, the most adversarial scenario will happen. So you better protect yourself against all of them. Okay, but then if you look at something that looks at verifying VST, very similar design to Daphne, except it doesn't care about totality. So termination is treated as optional. And programs are allowed non-terminate. And actually, non-terminating program is your best friend, because if it doesn't terminate, anything could hold at the end of it. Makes verification very easy. But we will talk more about that. So now if we go to the space of tools that are considering verification to be more of a bug finding, so we see another combination. So for example, in N4, we still have symbolic treatment of states, but bugs are actually looked. So what you're looking for proof is, rather than absence of bugs, you want to show the presence of bugs. So you actually want to prove the statement like exist an execution of the program that ends in dividing by 0, throwing an exception or something like that. And related to that, if your program uses non-deterministic choice or like it draws from, you actually want to find that exact path that leads to the bug. Don't care about the others. So that's why the existential treatment versus the others. And finally, quick check is just executing program on many inputs until it crashes, and it also neatly fits in this space, except, well, it obviously requires the concrete space rather than symbolic one. Okay, so this is something that is used to understand, but why does it help us? How does it help us to build the tool? Well, we kind of took all these considerations and trying to build a verifier that shows several design points on this space, and some of them are not even mutually exclusive. And this is just one instance of the library that accounts for all these possibilities, and there will be others. Okay, so Velvet is a verification framework that combines automated capabilities of Daphne with interactive proof mode a la Coq and a bug finding capabilities of Infer and quick check. So it can serve both of the symbolic and the concrete testing. How? Well, that's what I'm going to talk about next. So it sits in this space, and for what we know, in the space of verifying imperative programs, Velvet is the first foundational verifier. So foundational is an important word here. It means that, so that's actually a great question. The difference between quick check and infer is that this one treats programs symbolically. It means that it actually can report false positives. So it can claim that something is a bug, whereas it's not a bug. Quick check runs the program. So when it reports the bug, it is actually a true bug. So which obviously is something that you want, because like it's not a great testing tool if it reports false bugs. The problem is that if you want to scale testing to the huge code bases, you want to do it like in a divide and conquer fashion, right? So you don't want to rerun the whole application again. Rather, you want to kind of, okay, the developer submits the diff. You want to check if something is wrong with the diff. It is a static analyzer. But when people say static analyzer, they usually think in terms of verifier. So if static analysis passes, there are no bugs. So this is a reverse static analyzer. That's the one that looks for bugs. Initially, it was a great question, by the way. It initially was marketed as like the traditional static analyzer, and then they realized that it's not sound. So they started to market it as a static bug finder. All right, so Velvet. So Velvet is built on Lean. And this is where interactive proofs meet automation such as SMT, grind, and ESOP, and we've seen the examples. Okay, so I think I've been speaking for half of this talk. Let's have some demo. Let's see how far we can get with it. I'm very conscious of time and the fact that everyone is tired. Okay, so those of you who have managed to open the project, you will probably see something like this. So if you look, so there is a folder called demo. Let me just jump straight to it. So this is what a program in Velvet looks like. And this is not exactly Lean, but this is Lean with macros. So remember, Lean is a very extensible language. So if you are not happy with how syntax of Lean looks, you can make your own syntax. And this is the syntax that allows us to encode imperative commutations. There's actually quite a bit happening here under the hood. So I'm going to show this thing, and if you strip all the makeup from this program, we will see quite a few things happening here. Specifically, you will see this do notation and things such as pure and whatnot, which are good indicators that there is some state passing happening here. And when passing happens, that usually means a monad, so that's a monadic program. So the nice thing about writing a program in the monadic style is the fact that it can be interpreted in more than one way. So, and here we have multiple interpretations of the same program. One interpretation is just a runnable. Is it too small is it fine if I do it, if I make it like this? Yeah, good. Yeah. Okay. So one interpretation, and this is just a runnable Lean code, which, believe it or not, it is. So discrete square root of 10 is 3. So, and we can see it here. So in fact, this is not an encoding of AST of program for which we need a separate interpreter. This is actually vanilla Lean program. So what you see is the result of running it natively within Lean itself. So actually, if you want to execute it, it's going to be pretty fast because it's run. Yeah. So you can compile it. Right. This is actually what's referred to as shallow embedding. So those of you, I mean, we can discuss it after the class, but shallow versus deep embedding is basically how do you implement a programming language A in a programming language B. Shallow means that programming language A is like just cleverly disguised. So it's in fact the programming language B. And the deep embedding means that, well, you do what they teach you to do in the compiler class, right? So you build lexer, parser, and you then do something with the AST. Okay, so this is a shallow embedding, which actually comes with lots of advantages and also some disadvantages, which we can discuss later, but it's runnable. Okay, so the nice thing is that another way to interpret this program, and this is something that is triggered by a specific macro that we have, is to compile it to a bunch of verification conditions. So this program, it already comes with, it has no precondition, which means the precondition is true, but it comes with this 2-3 post condition, which basically collectively ensures that this is indeed a valid discrete square root of the program. And as always, the loop comes with a loop invariant. Okay, yes. So remember how if you look at the program, you can think of it as, oh, that's something that I'm going to run. And this is something that you run and get the result, provided the concrete input. That's one interpretation, a concrete one. Another interpretation is what we have done 45 minutes ago when we were computing the weakest precondition. That's interpretation. That's how you perceive the syntax of the program, right? So we actually want to have them together. And what we even want more, although this is not something that if you just use this tool care about, we want to make sure that all these interpretations, they are consistent with each other. So they do not contradict. So in fact, if we manage to prove something using the weakest precondition calculus, that should not contradict to what we will observe if we just run this program. So that, for example, like we need to account for all possible executions. That's called soundness. When you hear about soundness of a program verifier or soundness or logic, so I'm just gonna piggyback on what Deepak was lecturing about. So that means that that means that if you have proven something with logic, you will not have surprises at the execution time. So there will be no behaviors of your program that came unaccounted. This is actually proven sound. And this is the part of a huge iceberg that you will not have to see if you're just using the tool. But that's how you get something that gives you much stronger guarantees than most of the verifiers out there, if not all of the verifiers out there. Okay, the other way to interpret this program is to a bunch of verification conditions. Because look, we have the post condition, we have the precondition, which is just true. So we might as well just compile this program into, well, in this case, 10 theorems. So it turns out that if we prove these 10 theorems, we verify this program. Okay, at this point, you can see that you have a lot of freedom. You can just roll up your sleeves. Okay, I have short ones, but like if you have long ones, you can roll them up and start proving them the way you have done it earlier today. I mean, there are better ways. So obviously we can use grind to prove as many of them as we can. Grind is very powerful. So it knocks off 5 of them. Yay. So now for the remaining one, okay, let's focus on this one. This is your standard Lean theorem, says that for all I, if this holds, then I is less or equal than 0. Is it the case? Yes, it is, right? Because x is 0. I mean, look, okay, math kind of works. Okay, so we can go and do this intro. We can substitute the variables. And then we can use a lemma, which is actually proven somewhere in the depths of MATLAB. That's good, yeah. It might have been because this is on old Lean. I think that, yeah, yes, right, yeah, exactly. Yeah, we really need to bump it up. But again, I'm making a point here. So obviously, if we just specifically bring in SMT, that will make a very quick work out of everything. In fact, I'm just gonna show you that, you see it here, it complains, oh, look, you have unsolved goals, right? So you have 5 goals unsolved. But the default solver, something that, that's it. All right. So you see, that's the beauty of decoupling your verification condition generator, turning program into a theorem from the way you prove this theorem, because now you have a bunch of tools to prove theorems, and you just need to produce these theorems. Okay, and this is an idea that I'm going to exploit over and over and over in the next half an hour. Someone had a question here? No? No, verification condition is generation is triggered by this macro proof correct by. So this is where, yeah, okay. So now like, okay, it doesn't lex, but so right here, you will see verification conditions. Yeah. So proof correct program name by generates a bunch of goals. Each corresponds to verification condition. It's your job then to prove them. It's so this is the program. Yes, it takes this program and it takes this specification, and yeah, and it turns them into these theorems. So far, so good. All with me? I think it does, but I forgot what's the name of it. So how to print this as a proof term. So yeah. Let me restore this. Yeah, okay, please. I don't want to read all this. Oh yeah. Is it? I think it's called yeah, there you go. Yes. Well, you just forced me to read the macro. So yeah, I don't do it willingly, typically. Okay, good. So so far so good. Everyone understands what's going on. So let's see how we can go further. Okay, so actually it turns out that we can have a lot of fun, and even the programs that have some interesting constructions are not within our reach. So this is actually one of my favorite programs for like how weird it is. So this takes a function on a finite domain. So because we have this constraint here from finite domain to Boolean, and effectively transforms that into array of all elements. Okay, there is no dark magic here because obviously the function from finite domain to Boolean is just a table from all the elements to true to false. So what we can do is we just go through one, like each of these elements and put them into array. But we are going to do it in a very like kind of quirky way. So look at this indifferent whatever face operator. It actually has a name. It's called Hilbert's choice operator, which is something that provers like Daphne have. And this is one of these program commands which is amazingly easy to have if you only have symbolic treatment of the program. So your program is a formula. And it's very difficult to support if you want to have actually runnable semantics. Because what it says here, it says, give me x such that s of x holds. And what is s? Well, s is this finite functions. So you see what we are going through. So we check while there's this function still is true on some elements. Let us pick an element on which this function is true. Let's add this element to our array result, and let's redefine our function. So now it's no longer defined on this element. Totally fine thing for mathematicians. If you try to write an interpreter for that, well, good luck with that. Well, I mean, okay, we did write, but there's like always a lot of magic happening because here we use existential quantification as a Boolean condition, which it has absolutely no right to be, but it is because we work with the function on the finite domain. So yeah, lots of interesting things, but just to show you that I'm not kidding here, so we can execute this program and we can extract the value. The reason why there is 0.1 because there is this mutable, and this is actually something that the tool sneakily transforms into additional states. So we actually, so the actual result is a couple of the state and the final result. So we need to extract it. Yeah, so probably we want to have some better experience. Turns out that this is a function which is very easy to verify for this particular post condition. The post condition says that elements are in our array if and only if they were in the initial snapshot of this function. S old is just S with old, and this is the convention how we can snapshot the immutable values at the start of the function. So far, so good. So you see, like, yeah. That means that the result of the extract is actually a pair for the reasons that it not only carries the final result, it also carries this S, and this is the artifact of it being mutable. Lean is actually very sneaky. It allows you to have mutable variables, but they are encoded as the implicit state that you pass around. Yeah, so yeah, that's why there's this additional shenanigan here. Okay, so this is something that is proven, just like that. So let's look at more examples of this of this operator. So this is an example where we try to withdraw a bunch of amounts from our balance, and we want to make sure that we reach the end, so we actually do not break. And the break happens if we try to withdraw more than the balance currently has. It's not the most interesting program in the world, but it kind of makes the point. So here is the program which kind of says, give me randomly a list of amounts that I want to withdraw from my account, but only such that together they do not exceed my balance. Which is kind of cool, right? So because we know thanks to this, we will not exceed our balance. So if we do this, so that will obviously fail to verify. So we will get an error in the proof. But with this nice refinement, okay, if you like refinement types, so these are refinement types. So this is refinement to and the non-deterministically picked variable. So this is kind of this is exactly the case of reasoning about choice non-deterministically. So it basically caters. So if I put true there, it protects me against the case when we actually pick the list of amounts such that they exceed the balance. However, what if this is exactly what we want? So what if we want to show that this program has a bug? So here is the version of this program that just does exactly this and says, well, pick whatever list. So what I just changed is that I changed the semantics of how we treat the choice. So from demonic, I changed it to angelic, and this is angelic is so these particular strings, there are specific keys. And then what I want to show is that my postcondition says that the result will be actually false. So at the result, we will get not success, meaning that we need to come here, right? And this is actually great because this is exactly what the bug finding tools like CBMC do. So they find that exact execution that leads us to this one. Yeah. So obviously to satisfy this angelic non-deterministic condition, someone needs to prove an existential quantifier because there exists a path. So this, you see, I'm actually at some point. So okay. So this is something that is obviously very easy to prove. So we just instantiate this existential. So that's actually so you see correctness and incorrectness are in the eye of the beholder. So a few years ago, 6, 7 to be precise, there was a big move in the programming language community because Peter Hearn rediscovered after some other people, no one really cares who they are. I mean, obviously everyone cares, but like people know Peter Hearn, so that's rediscovered what's called incorrectness reasoning, which is effectively a treatment of symbolic model check, symbolic execution from the perspective of Hoare logic. So Hoare logic says that, like, okay, nothing bad has happened. So which is universal quantification for all executions. Good, right? Now we want to switch from universal to existential, right? Okay, let's give it a name. It's called incorrectness logic, and this is what for the past 6 years people refer to incorrectness reasoning. But in fact, this is what CLI and CPMC have been doing for years as symbolic execution tools. The point is, we can have both. Isn't that amazing? Pick function, well, it's okay. So work here is not completely. So your question is ill-formed because when you ask how pick function works, I can interpret how does it run, or what's the verification condition generator for it does. Which one is it?
Second.
So second one. It depends on how you interpret. So let me try not to mess it up. So for okay, so Ex assign click. I'm going to be very non-specific here. If you want, okay, so in the case of demonic non-determinism, that means that's the demonic, right? And in the case of angelic, I don't know how to know an angel, something like this. I don't know, that's an angel. So in this case, it's like this. So these are two different interpretations.
The pick turns into some quantifier.
Exactly.
Depending on.
Yeah, but that's why I'm saying like implementing peak symbolic and orders of magnitude easier than implementing peak concretely. Because if you want to probably like enumerate all the possible ways you need to like synthesize decidable instances and do stuff like that. Did I answer the question? Okay, wonderful. Okay, let's look at more fun things. I mean, you can obviously nest statements. So, I mean, if you have a sequential composition, you will get more of them, right? So don't ask me if you can have angelic and demonic interpretation of different peaks in the same program. I know that this is what trying to fuzz my presentation usually. I don't know. I mean, someone asked us before, we scratched our head, we didn't come up why it would be useful, and then we sort of give up. So great point. So there are probabilistic interpretations. Okay, so obviously, I mean, programming languages researchers wouldn't be themselves if they didn't find the least relevant problem which has the most interest in semantics and try to solve it. So now I think 30% of the Popol community is building a reasoned methods where this has a probability attached to it. So that whole thing compiles not just to the logical formula, but on the assertion that involves probabilities and whose semantics and in terms of expectations or stuff like that. We looked into that, but we have finite amount of time, so that's something that we will do next. But yeah, so if you don't care about that much about shallow embedding automation and you just want to study the semantics of it, there is no, like every Popol has like 3-4 papers on the probabilistic core reasoning for different properties. So yeah. Okay, wonderful. So let me show you a couple of more things. We're doing on time, actually pretty good. So okay, so here's another thing. So everyone's favorite program, insertion sort, ported directly from Daphne. So this is insertion sort. Actually, those of you who probably took CS 101 N years ago and never taught it since then might not remember why insertion sort exactly works. And writing invariants for insertion sort usually prompts you to remember why exactly it works and how it keeps sorting the prefix. And this is what we have, so that for any, so up to I, everything is sorted. And then within the prefix, everything is on the left is smaller than the element that we are holding right now. So these are invariants. So as you can see, they form more than a half of the program itself. But once we have stated the invariants, okay, we can verify the program, but let's do something more fun. Let's test the program, because when the invariants are so large, it's actually relatively easy to mess up even the specification itself. So you see, I just changed less or equal to less than, and this is something that, okay, it broke verification, but more importantly, let me do something like this. Something like this, and we run this. Trying to think what would be the interesting bug to introduce. Yeah. Okay. Let me do something more egregious. Yes. Okay. So here's the one. So this is interesting. So what did we do here? So in fact, we did test our program, and we actually showed that the specification is violated by this very specific randomly generated array. So this is exactly what in software engineering people call fuzzing, but in our case, this is what the plausible tool does. So plausible is something that Lean supplies as a part of the standard library to implement randomized testing. So now we can go back and restore that, and it actually does verify. Actually, it doesn't verify because my invariants are still broken. Okay, so now it should verify. So one problem is that since we use grind, and this is fairly old one, so this is not as fast as it could be. I'm going to talk about that. Okay, now I'm going to test how well you remember what I've said at the very, very early in this lecture. So I'm going to first comment this one, and then I'm going to comment this one. And the question to you, will this program still verify? Well, okay. Let me remind you. If it terminates, it finishes in some state satisfying Q. So this is actually a crucial difference. Your verifier verifiers are actually very sensitive to how you treat termination, because non-terminating program is the program that reaches any state. This is also the reason why Lean is so picky about termination, because if you start using non-terminating programs in your proof, that program might have false postcondition, and this is how you can prove false. So you don't want to prove false only. That makes it useless. So the point is, oftentimes proving functional correctness, namely that the program doesn't crash or doesn't do anything bad, is so important. Is that and proving termination is something that people think that they would discover one way or another. Or termination is just extra hassle because you need to mount an additional argument that usually has to do with identifying termination measure and whatnot. Oftentimes people just go with this style, and it's called partial correctness. And yes, as has been suggested, this proof goes through. Okay, so now let me do just one trick and switch from this to this. Okay, so first of all, I get a massive complaints that, oh yeah, now you need to provide me, so some tools like Daphne, they're actually very good at inferring termination measures. So termination measure is a very simple idea. If you want to show that your loop actually terminates, abolition. You also need to call this one. But if you start from invariance and u and some duplicated variable of v for variant equal to some fixed value, then after you execute your value of the loop, you have this. And also you have I implies v is larger than some constant, so it doesn't decrease for it. But it has to be found available. But in Dell's effects, there's some way to say that something is well found. No theory. So yes. Right. Okay. So you see, this just kind of gives you yet another proof obligation to tackle. So you need to provide something that decreases, right? So one way to phrase it is that I give me some quantity that with each iteration goes down. And Daphne and other verifiers can infer them, but not always. So we do not infer them, we just ask to provide them. So you see, as you iterate through the array in the insertion sort, the size of the suffix of the array goes down. So that's exactly the termination measure for the outer loop. For the inner loop, this is just the index that is being decreased, right? So from where you started till the beginning of the array. So now you provided this too, and predictably, the proof now breaks. And very pleasantly, it breaks with actually really a reasonable verification condition that it cannot prove, which exactly has to do, see, there's an inequality there. So this is the same, this is exactly this inequality. This is what is not capable to prove. Again, just to give you I think it's simple, it's well to understand it. This is verbatim how the verifier works. So it just keeps compiling the programs and specifications to Lean theorems, and we are experiencing this in theory. This is the multimodality, and whenever we can,
This is broken in the case where you commented out.
Yeah, exactly. Yeah. So I'm gonna bring it back.
Termination method.
Yeah, I'm gonna bring it back.
How it works.
Not yet, but rumble. Yes, it works. So yes, so we this is an old version of grind, which is quite slow. So yeah. So yeah. Actually, I'm wondering if okay. Because inferring termination conditions is undecidable in general. Not necessarily. I mean, it's not required for partial correctness. How exactly you phrase your termination measures, that's up to you. So this is the syntax that Daphne has adopted, and we are following it in the same way, just not to confuse people. So in Lean, I think it's called terminates by, decrease, but termination by, and then decreasing, and then yeah, something like that. So okay, that's in vanilla Lean. Okay, so that was total versus partial correctness. Actually, something that is even better. So let me just go and show you. All right, so this is actually a very interesting lemma that we have. It's a meta lemma that the framework provides you. It says, and it might look kind of clunky, but this is actually very interesting from the ergonomics perspective. So you see, as I said, partial and total correctness, sometimes you want partial. When you want total, you probably want partial too, but it's nice when you can have a division of labor. So this theorem says that if you give me two programs that are exactly the same, if we erase all the annotations, then if you prove the program being partial, and also that this program terminates with the post condition that is absolutely non-informative, then you know that this program is totally correct with this regard. I think this is beautiful. So, and the fact that you can have it as a meta theorem, which as itself is proven. So this is not a hack. This is not a rule that we have kind of axiomatized on the paper and decided, okay, let's have it, which would be the case in the vast majority of other frameworks. This is us building verifier out of collection of facts about semantics and logical interpretation of program specifications and how they execute. So what I like to say to practitioners is the Lean is the world's best meta verifier because you can use it as a language to build your own verifiers on top of it. Let me just repeat it. So that means that these two programs are equivalent up to erasing all the annotations, pre, post conditions, and invariants. Okay, so just to show you how it works in practice, not as elegant as in a single slide, but this is all, by the way, committed. You can study. So here's the insertion sort, which is partial. And here we have a partial semantics, and we have already discussed that, and it's just verified. And then we have the one in a different section, which is verified for the total correctness. You can see it's much simpler post-condition. And in fact, that's the pleasant thing that we actually don't care whether it sorts correctly or it doesn't. The only thing we care is whether it has termination measures that make it terminate. So same, I mean, probably with a little bit of macro hacking, we don't even have to write the same program twice. But this is like if there are people who are human-computer interaction research inclined in this room, and you are interested in how to make verifier experience more pleasant, well, I'm very interested to discuss that. So this is just what we've got. And then we have this insertion sort, which is the final one. And this one actually is under the total correctness. And the nice thing is that you see it doesn't even have any invariance. So we only think we need to know is to use this theorem and provide these two programs, which are automatically shown to be equivalent up to erasure, because syntactically they are the same. And then we have these two triples, which is what you asked, how to get the exact proof term. So underscore correct from these two. Yeah, but like, I mean, they need to be like differentially equal, like after you have done it. Yes. All right. Okay, so I'm nearly there. So one other thing that I want to show is that if you are doing this sort of verification, oftentimes it gives you very nice divide and conquer principle in how you want to verify your computation. So imagine that you have some hairy imperative code that does something effective, dynamic programming, but not like matrix manipulation. And you want to show that it does that correctly. For example, our favorite example that we have is multiplying sparse matrices. So sparse matrices are matrices that are encoded through a series of compressed arrays. So naturally, if you try to multiply two matrices that are represented by compressed arrays, you're going to have very intricate programs, right? So what we can do is that we want to show that these two things multiply matrices correctly. So you have some preconditions, typically a trivial one, and you have some mathematical property that you want to show that holds with regard to the result and the argument of your imperative program. What you want to do is you want to employ both verification engineers who know about program verification and mathematicians, or just two different AI agents, I don't know. So, and the way you can do it is by divide and conquer, which is actually a really elegant idea that has been used without a name for many decades in program verification. And then Andrew Appel, the professor in Princeton who led VST, gave it a name, a two-stage verification. So the idea is two-layer verification. So the idea is very simple. So you try, so first you come up with a mathematical function that captures the workings of your imperative one without like doing so imperative. So this is pure Lean function, something that starts with def. This is imperative code. This is the statement that you want to prove. Turns out that this statement is actually much easier to prove than the general property of this function. So you show that this function satisfies this property. This is usually a hard mathematical proof. But the nice thing is this proof knows absolutely nothing about your loops, pointers, arrays, and whatnot. This is just something that a mathematical proof agent like Aristotle can do. And then you have the Wikiman rule that basically says that since this holds and this holds too. And this is actually something that allows to structure verification quite nicely. So I'm going to give a very short glimpse of what does it look like. So we have this example of sparse matrix multiplication. I'm just gonna go through a bunch of steps without explaining what is happening. So first, we have a pure function that does something relatively ineffective on the representation of matrices by certain data structures. And this is going to be our main culprit, because the next thing I'm going to do is that I'm going to show that this pretty hairy imperative program effectively refines these pure functions. And this is in the postcondition. So to make this proof work, and this is something actually quite interesting, I'm going to prove a bunch of facts about the pure function itself. So this is a pattern which is very familiar to people who work with verifiers like Daphne. So typically, if your proof doesn't go through automatically, you define a bunch of axioms that you strongly believe are true, and then you make the SMT solver aware of this axiom. So like now beefed up with these axioms, it just goes and proves on. We are in Lean, so we don't want to extend our trusted code base. We can just prove those axioms as lemmas and give them as hints to our solver. So now with these hints given to grind, this thing is actually given to SMT in this case, this proof is automated. So we are done with proving that our imperative code implements the functional code. And from here point on, and this is where the large part of the file is, we go and construct like really ungodly proofs of the property that we want. The nice thing is that at this point, we are fully out of the programming world. So we are back to the mathematical reasoning, to the pure reasoning. And this is actually something that goes on. And after we are done with this hellish thing, so effectively, this is exercising the rule of consequence that's saying that our program does indeed satisfy like that property that we are struggling to prove. Okay, so the idea is, again, divide and conquer. So do mathematics with mathematical functions, do proofs over programs with regard to mathematical objects. Works really well as a division of labor. I'm almost out of time, so I'm going to show last example that I like a lot. So, and this is one, since we started to talk about the division of labor, this is how things go. So this is actually an interesting program, because this one is from the project that we have done recently on the verified program synthesis. So, I mean, when during the COVID, I practiced my coding skills because I didn't know whether this professor thing is going to work out. So I thought, okay, maybe I should like really learn how to program and solved a bunch of lead code tasks. Some, I don't know, like 50, 70, don't remember. It was fun. So obviously times have changed. So now we can like LLM solve lead code. The question is, can they prove lead code? So, and this is something that we have done. So we have just given a bunch of prompts and examples from lead code. And we have asked LLM to synthesize everything, including the specifications, at which point you should think, do you really want to vibe code your specifications? The answer is that you probably don't, but that's an interesting research on its own, how to convince yourself that your vibe coded specification is actually a legit one. If someone is interested, we can talk about that. But again, this is the vibe coded specification on a function that says whether the number is prime or not. And the specification itself is executable, but it's very inefficient. It just counts the divisors. Slightly more efficient one would go to the square root of the number and check the divisors up until the discrete square root. And this is exactly what this program does. Okay, and now the interesting part. So this is not a very difficult program. So now when we try to go and when we try to verify it from the first principles, I've just removed all the automation. We are met with 15 verification conditions. So obviously, many of them are absolutely stupid. So SMT and grind made quick work out of them, and they leave us with one. And now looking at this one, we can appreciate that this one is actually not entirely trivial. What does it say? It says, like, if we look at every number d between 2 and what is the square root of n, and the number of such d's that are divisors of n is 0, then this number is prime. Okay, this is actually a number theoretical fact. So, I mean, probably somewhere in MATLAB there is a proof of it, maybe not. But at this point, what we want to do is realize that, okay, our automation is not going to cut it. What's going to cut it? Yes, you know the answer. So we are extracting this thing just like that, from our info view to a separate theorem and give it to the AI agent of choice. And luckily, there are no shortage of AI agents that are very, very good in writing proofs over MATLib. They're very bad at writing proofs with domain-specific reasoning, but that's why we build a framework with a lot of automation. So the program-specific reasoning is gone, only math remains. And now, also, once this proof done, we can just plug it here. And this is actually something that scales remarkably well. So when we developed the first version of Velvet, one of my students went for Christmas break back home to China, and there was a program verification competition in Beijing, where I don't know how the organizers gave one task in Velvet, which was open source, but we did not advertise it. And the task was to verify memory allocator. So, and this is what was given, but it was given without invariance and whatnot. So, and sure enough, we have, I mean, I'm not going to explain what this memory allocator does. We all kind of have a rough idea of how memory allocators work, like free list and whatnot. So obviously we hit it with automation, and it produces 40-something goals, solves most of them, and leaves 7. And most of them are pretty trivial, but there is this goal 6, which obviously proven with AI. But the crazy part, and this was Claude 4.4, 4.5, it was fairly old. For proving this one, it effectively engineered the whole small library of to reason about a circular path in the free memory list. So amazing stuff. So now, I mean, now we can write like imperative code, and we can have all this mathematical discovery at the tips of our fingers. Okay, so that kind of concludes the demo. I also was planning to tell that Velvet is, like, in the version that I'm showing is pretty slow, and there are good reasons for that, because native automation in Lean before the last couple of versions is not great, but luckily Velvet 2.0 is coming, so we will release it in maybe in a month, and this one builds. So first of all, the good news, that framework about weakest precondition monads and other goodies, that's now part of Lean official. So we first wrote it as a paper, and now it has been merged into Lean since 4.31. So now Lean has this monad for efficient proof automation called SimM, which blends many steps together without reconstructing proof terms. So this is, and use hash constant and other things. So, and this is actually something that helped to optimize grind and also domain-specific automation quite a bit. So, so blue is Daphne, which is basically like unbeatable state of the art. Green is Velvet 2, and as you can see, we are like almost everywhere. We're at least as fast as Daphne. And I think we should, like, I just invite you to pause for a second and think like Daphne is just a wrapper that prints your program to SMT and uses SMT. Lean and Velvet do transformations from higher order logic to something that grind can solve it and produce the certificates, the proof term of what have been proven. So it actually is something that gives you like infinitely stronger guarantees than auto-active tools. And now this is something available. Okay, so yeah, and there's some statistics from my students. Okay, so just to take away, what we have seen today is a multimodal program verifier written in Lean, foundational, meaning that as the verifier it's sound, if you prove that, you know, it actually holds over the programs you run, well, modular Lean compiler correctness, I guess. It's fast, and it connects the AI for math progress to verification of imperative programs. So this is what you can get it if you're interested. I'm going to share this slide. So this is the paper that is coming up next month, actually this month, on the design. It's all on my webpage, so you can find it, and on the page of the lab. So this is the paper that has lots of monads in it, if you're interested how that works underneath. And this is the upcoming paper, which shows how you want to combine it with AI to save lots of tokens. Define programmer. Are they written by a human? Not necessarily. We live in a fantastic time. Everything is automated. The question is like, does something or someone needs to write them? Yes, that's the case. We are all of that. So yeah, yeah. The point is that this law is not really evolved, but we just like regress to interactive book solutions. Yeah, which is something which is much more problematic than Daphne Barons and everything that if you just around this. So
Velvet is closest to its actual language. Which is closest what? The syntax of Velvet is closest to its actual. I mean, you have designed your own imperative language.
I mean, that's like, I mean, the inspiration too, and we usually, the experiment was done with Daphne and Lean. And then the syntax sort of stuck, and Daphne syntax is something that many people know anyways. But it's just a matrix. We can go and make your own syntax.
The point was like, I wanted to ask, like, how big runs the program that you verified as right?
Oh, and then actually, one of my students is currently working on writing a substantial system in it, and that actually prompts us to improve the verifier as we go. In terms of big, I don't. Why everyone just so fixated on the lines of code? So in terms of big, I don't know what to tell. We actually have lots of cool programs from lead code. So, and here are some of the interesting ones. So like this find majority element. That's not a trivial one. So, okay, or is sublist. This is all obviously automatically generated. So if you're interested in generating interesting algorithmic solutions, I think we're already there. If you're interested in generating Firefox, maybe we should first learn how to specify Firefox. This is the very specific goal to actually pull the refinement variables. So Velvet is kind of the bedrock already. So the large vision is that in the future, Ling will be one of the dominant languages. So we might as well build the infrastructure that make it more like easier to adapt to different styles of problem, not just the functional problem. So that's step important, but doesn't mean that everything should happen at this level. Some things happen different levels of abstraction, so we won't find begin those properties. And so that's why we decided to put C.
So you need to ask about the distribution of the proofs that have a velocity.
Fascinating question. If you talk to him on my blog, he is an expert in that.
In fact, two related questions. When you said macro, did you mean literally macro, not elaborators in the syntax?
Elaborate, yes.
Oh, you meant it.
Elaborate, yes.
So when you say in Spencers and so on, does that translate to something in Lean, or it's part of Velvet? And then so standard Lean has def.
Yeah.
You have this method so and so.
Yeah.
But after that return and ensure statement, at what level of is that? Is that part of Loom, part of
It's a part of Loom, so we have this gadgets which have different interpretations, so they have no computational meaning, but they obviously contribute to this preconditions there, right?
Right. So suppose we use the standard Lean syntax or the and so on, like this loop as part of Lean.
Yeah.
Then can we use these extra data like return and ensures in Loom with standard Lean syntax?
That's a great question. I think you should ask it on Velvet.
It's Velvet.
Yes, yeah.
Can do that.
Yeah, I mean, as you can imagine, being a faculty means there are certain things about the system that I don't know. So
Sure.
how it's implemented. But yeah. So the interesting part of that, so the MVC gen only supporting extrinsic proof, so you actually need to provide the invariants in the code. So here, when we are allowed to provide it in the program itself, which comes the advantage that, for example, you can test. You can test your invariant.
Right.
So it's difficult to test your invariant because it's people the same.
But you check it's the same thing, which is used every in a multi-modal.
Yeah, so this paper that I suggest look, it actually tells a little bit about the runtime representation of all this, because we rely a lot on property-based testing to filter out bad candidates. Yeah. The one with what?
The green bar development 2.0.
Sure.
Benchmarks where it will not upload the app. That's the I think.
Yeah, that's a good question. Again, you can ask on the Zulip channel. I don't know why. I mean, okay, it's already 10 times faster than it was used to be, but it's still not as fast as Daphne. I get okay. Yeah, I know the reason. So Daphne has a very fine-tuned heuristics for triggers. So basic triggers. So trigger is something that indicates whether you should apply an axiom when you try to prove the statement. Okay, you have a statement and you have a bunch of hypotheses, and they're all of the form for x, like p of x. So and you have p of x somewhere in your context. Do you apply that, or you apply something else, and you have multiple candidates? So this mechanism of deciding what to apply is called triggers. This is something that SMT solvers actually allow you to specify. And Daphne, so there is a nice paper from CRAFT 2016 by Rustam Lane and Clement Pitt Laudel about these heuristics of choosing triggers. And I think this just falls into the class for which just look for like Rustam Lane and CAF 2016. Yeah. Falls into this class where triggers are a little bit more and better. So in our case, it's fine. It's just like not fine piece for that like better edit. The nice thing about benchmarks that don't really need to beat on every single one on this reason track. Yes, sir. So there is syntax that you see on the screen, and there is the way that it encoded in terms of lean definitions. And obviously, I'm saying that this is vanilla lean, but obviously it's vanilla lean that, well, is decorated with some specific data structure, such as when we write the invariant that has an adherence in the program. And this appearance is something that comes out of syntax. So
essentially transfer.
yes, yeah. Yeah, so people actually, an interesting question which you usually get is like, how do you know that your elaboration is correct? And I don't have a good answer. I don't know how to verify elaborators. What I know is that since it's so embedded, you can just run your program and you can see if what you're getting is what you expect. And once you're convinced enough that your elaborator actually produces the program that behaves predictably, that's when it starts verifying.
Other questions? We have a Q&A tomorrow morning as well, and to ask parts to the
Yes, that's right. So part 2 is coming tomorrow on distributed system. So see you.
okay. Forget that. But in terms of like this, the tag is loaded. When you're writing is variance and basing it all, you just take those things and use them as beneficial they can understand folks can do, but you don't do anything apart from that. For proving correctness.
I'm not sure fully understand the question, but I feel like this. Everyone is eager to have a dinner, so let's discuss it right now. So happy New Year's, everyone else.